permutations. What exactly is a permutation? Okay, well, the most common way that permutations are described is that you're counting the number of ways in which items can be arranged. And while that is true, and we'll talk about the specifics of why that's the case in a second, I think you're going to find it immensely more helpful for understanding how to count if you look at permutations from the perspective of, so in the videos where we talked about the product rule, the idea was you had these different events, which you could think about as these different slots. Okay, so for example, we looked at the idea of what we're trying to make a sandwich with, we can choose from 4 different types of bread, 3 different meats, 3 different cheeses, and 2 different condiments. Okay, and then we wanted to then count the total number of different types of sandwiches we could make, unique sandwiches. Well, then the product rule says that if one event can occur this number of ways, and another event can occur this number of ways, and another event can occur this number of ways, for however many events, then the total number of ways that those events can occur together at the same time, so not separately, it's like an and statement is the key to the product rule. It's not how many different ways could we choose one of 4 breads, or one of 3 meats, or one of 3 cheeses, or one of 2 condiments. It's how many different ways could we choose one of 4 breads, and one of 3 meats, and one of 3 cheeses. This is all occurring at the same time because it makes up a sandwich. Then to count the total number of ways these events can occur together, you multiply them. 4 times 3 times 3 times 2. So you have that many different sandwiches. Okay, now we're going to see that to develop the formulas for permutations, counting the number of arrangements, we're going to use the product rule. And we're going to use it in a way it's going to look just like what we're doing here. But this is not a permutations problem. And the reason why it's not is because for each of these events, we're not pulling from the same group. These groups are different. They're completely distinct groups. This is bread. This is meat. We can't choose a meat here. Okay, but with permutations and combinations and permutations it's the exact same kind of goal you're trying to accomplish in terms of counting arrangements. Just combinations has a different feature to it. But with permutations and combinations, each of these slots you're picking from the same group. That's the difference. That's the key feature you want to keep in mind. Now, however, when I say picking from the same group, to be technically correct, you could be picking from the same group or picking from groups that are dynamically updating based on what you chose in the prior group. So if I'm picking from a group of 10 basketball players, and I'm picking from a group of 50 basketball players, and I want to pick a team of 5. Okay, well, so here's that group of 50 players. Well, okay, I'm picking from the same group for these slots, but it's like dynamically updating. I pick a player, okay, they go here, so Tim. Now, for the next slot, it's technically not the same group as the first slot because now it's this new group of 49. That doesn't include Tim. But in essence, it's the same group, right? It's just because this group is a function of the previous group. So that's a permutations problem, a combinations problem. Okay, so let's forget about the idea of combinations for the moment and look here at a basic permutations problem. We've got a group of 5 men and women, so Tim, Sally, Kristen, Philip, Morgan. Okay, this group of 5 people, and we want to know how many different ways can we arrange these 5 people in a line? So how do we determine this? Well, okay, we just need to use the product rule. With the product rule, we can think about how, okay, here's the 5 slots in line. In the first slot, this can occur 5 different ways. We could pick 1, 2, 3, 4, 5 different people. There's 5 different ways that this first event can occur. Now, just note, I'm saying events, which might make you think back to the Venn diagram, right? We have these different events, event 1, event 2, etc. And each of these have a number of different occurrences, and we could multiply the events, add the events, depending on the circumstances. However, permutations and combinations are a little difficult to use with Venn diagrams because the events are connected. So yes, they're overlapping, but it's not even just overlapping. The outcomes are dynamically related to one another. So it's hard to apply a Venn diagram in the case of a permutations combinations problem. But the way you would look at a Venn diagram in relation to permutations and combinations is that this event 1, this entire event 1 might be this problem here. How many different ways can you arrange these 5 people in a line? So we go off to another page of our notebook, do this whole problem, get the count, and that count is in, and we put that in here, and then we relate that to another event that's separate. Okay? So this first event can occur 5 different ways. Now, how many different ways can this second event occur? Well, there's 4 different people to choose from at this point. We've chosen 1. Now there's 4 different people to choose from. And we're going to want to multiply these because the question is, how many different ways can event 1 and event 2 occur at the same time? Because we're thinking about arranging these people at the same time in a line. Okay, so now the third event can occur 3 different ways because, okay, it's like we've chosen Tim. We chose Tim first. Then we chose Morgan. Okay, so now there's 3 different options left. Sally, Philip, and Kristen. So this is, you have 2 options left, and then finally you have 1 option left. And that's it. That's going to be the total number of ways we can arrange these 5 people. We just multiply this out. And what you can see is that this is equal to 5 factorial. Now, what's important to note here is that we are counting the idea of, so if we had Tim first, then Sally second, and then whatever else, well, we're also counting if Sally was first and Tim was second, right? That's the different arrangements. The order matters here. That's the whole point of this, okay? But it's important to note, though, that we were not, when it came to the sandwich, if we chose wheat bread, bologna, Swiss cheese, and mustard, we were absolutely not counting the total count. When we multiplied those 4 numbers out for the sandwich, we were not counting the idea of if B was first and W was second. Absolutely not. Because those events were completely distinct. You couldn't choose bologna for the first slot. It would make no sense to have Swiss cheese in the condiment slot. The only reason why the different arrangements are counted here is because we're pulling from the same group for all of these events. So, okay, if we pulled, looking at one example, if we chose Philip first, then we chose Kristen. Okay, that's fine. But we started off by counting that there was 5 different possibilities. We could have chosen from anyone here. This could have been Kristen. This could have been anybody, this first slot. And then this could have been Philip. You see the difference? This was anyone from the group. So it makes sense that we're counting the different arrangements. Okay? And so the most basic permutations problem is you've got in objects, in people, in whatever. So in items to arrange, and you're going to arrange these in a line. You could also think about arranging items in a circle, like around a table, and that's slightly different. We'll talk about that in a second. But you're going to arrange these in items in a line, and you just want to calculate all the different ways you can arrange them. That's the most basic permutations problem. And the answer to this question is just n factorial. Okay, now we can increase the complexity of this a little bit, this basic permutations idea. We can increase the complexity a little bit without really going too far from just a fundamental permutation by thinking about, so if we had, let's say, a group of 50 basketball players, so you've got this group of 50 basketball players, and we want to choose a team of 5 from this 50. Okay, in that case, how many different arrangements are possible? And we're saying that order matters. So this is the point guard, the shooting guard, small forward, center. So order matters. If we put Tim here and Philip here, but then switch those spots, we want to look at that as a different team. Okay, but we can choose Tim, Philip, Kristen, etc., but then switch somebody that wasn't originally chosen in here and put them in the different slots. We want to count everything. So how do we do this? Well, okay, we start with the product rule, and we think about, so for the first slot, there's 50 different possible outcomes. We can choose any of the 50 players. Okay, the second slot, there's 49. Third slot, there's 48. Then 47, then 46. And we're going to multiply these. And that's it. If we multiply these out, that will give us the correct answer. And you can think about how this accounts for all of the arrangements, because this first slot could have been anybody in this entire group. This second slot could have been any of the remaining 49. But it also accounts for the rearrangements. That this could have been, you could have chosen Philip first, then Tim second. But this could have been anyone to start with. So it accounts for the rearrangements. And it accounts for everybody in the entire group. Okay, and now a problem like this is the more general fundamental permutations problem. Just a pure fundamental permutation is this kind of problem where you're choosing from a group that has size equal to or greater than the number of ways you're wanting to arrange the items of that group in a line. And so this is what's thought of as a fundamental permutation, which is so you have it's written like this, NPR. You're seeing the number of ways to line up R items in a line, choosing from a group of size N. So in this case, we would be wanting to find 50 P5. Okay, but the key with a permutation, though, is that the order matters. Okay, and so, but what's the general formula? Well, the idea is you think about this as you start off by saying, okay, what's the total number of ways to arrange these 50 items in a line? Well, it's 50 factorial, right? But we don't want to arrange all 50 items in a line. It's just the first 5 items that we've chosen from the 50. So we want to divide out all of the 45 arrangements that we're not using. And that's going to result in what we're looking for. Why is that? Because, well, what is 50 factorial? Right? You can write 50 factorial this way. These two cancel out, and there you go. Okay, so the general NPR formula is n factorial over n minus r factorial. Okay, now, can permutations problems have more complexities than just this here, than just this formula? Yes, absolutely. However, it's still important to just recognize the fundamental basic permutation, because with any problem, you're always going to pick out, okay, look, I see that fundamental basic permutation, and then you'll analyze, okay, what are the additional add-ons I need to factor in here to get the correct answer, but you're still going to start by recognizing that you're dealing with a fundamental permutation. Okay, now, but note that this formula includes the case where you have a group of 5 items and you just want to think about how to arrange those 5 items in 5 slots. Because in that case, you've got, so you're choosing from 5, a group of 5, you're going to arrange them 5 ways. So that's 5 factorial over 5 minus 5 factorial, 0 factorial. 0 factorial is 1. So there you go. So it includes that case as well. Now, in regards to arranging objects or items or people, not in a line, but in a circle, so kind of like around a table, the number of different arrangements in that case, I actually want to come back to this in a later video. I think it'll be better if we talk about combinations in the division rule first.